This conference will now be recorded.
Hello everyone. So we'll start with the nomenclature of haloalkanes, and then there will be some problems related to it. After that, the topics that we'll discuss, parameters related to the CX bond, that is carbon halogen bond, and physical properties of this type of compounds, and if time permits, then also the preparation methods for haloalkanes. Nomenclature of haloalkanes. So in last day, we have seen that three types of systems are there: common system, IUPAC system, and trivial names. And among these two, in common names, there will be some rules, but mostly the rules that are strictly followed, that are IUPAC system. Fine. So here we will discuss common system and IUPAC system, because trivial names is all about the discoverer names or the place where it is discovered. Fine. So common system, when we apply, then the method that we follow, that here alkyl group is named first, followed by chloride or bromide. So depending on how many carbon atoms are present in the alkyl group, if it is one carbon, it is methyl, two carbon ethyl, like this. And after that, you have to write the name of the halogen with ending with IDE, chloride, bromide, fluoride, like this. Now, this common system, when we write these names, see here we have two parts. One is the alkyl group, another one is the term that are related to the halogen. So there are two terms, but remember these two words that we will use, that will be separated. So this is not a single word. It is always written as two separate words. So two terms will be pronounced separately. So see here in this table, we have some compounds in the left hand side, and then we have common name. After that, we also have IUPAC name, but we will come to that point later. First, here focus on this common name. Here the first molecule is very simple, CH3Cl. So here the alkyl part is methyl. So first we have to write methyl. After that it is chloride. So see, here two separate words are mentioned. It is not that it is a single word. It is two terms. Next we have two carbon chain. So that is why it is ethyl and then bromide. After that, the third one, CH3CMe2. So this compound is like this basically. That is H3C, that is attached to carbon, two more methyl group, and then it is bromine. Now this total group, it is known as tertiary butyl group. So that is, it is mentioned tertiary butyl, and then it is bromide. Then CHCl3. Now here the common that is the way that we are writing until now, that is up to this part we are doing. First we are writing the alkyl part, then it is the halide part, but in this case it is something different. Okay, so this is a special case. Here the name is chloroform. So this name is used, it is so frequently used that mostly we use this term, though it is not following this alkyl halide, this type of term, but this is the most commonly used term for this molecule. Then we have CH3CHBr2. CH3CHBr2 means CH3 group attached to CH and then 2 bromine. So this is basically gem dihalide. Remember, when both the halogen are attached to the same carbon, that is known as gem dihalide, and this part is known as ethylidene. So ethylidene and then bromide. What is the difference with ethylene? That is ethyl. When it is ethyl, it is basically CH3CH2 and only one Br. But here it is CH3CH and two halogen. So it is having different term. It is ethylidene. And then we have allyl group CH211CH2 and then I. So that is, it is allyl and then iodide. And after that we will see the IUPAC. So when it is IUPAC name, alkyl halides are named as haloalkane. Now see, this is a single term. There is no gap, halo and then without giving any gap, alkane. First we are mentioning the halo and then alkane. It is not same as common system, it is completely different. So this is named as haloalkane, and the other rules now we will see one by one. So first step, what you have to do, you have to select the longest chain of the carbon atoms that is containing the halogen atom. So it is not just enough you are choosing the longest chain. you also have to keep in mind that the longest chain should contain the halogen atom. Otherwise, it will not be the correct way to choose the longest chain. After that, we have to number the carbons, but keeping in mind that minimum number should be given to that carbon with which halogen atom is attached. That point is also important. Now, sometimes it may happen that in the alkyl chain, there is some CC double bond or triple bonds are present. Then what to do? Then you have to give importance to this double and triple bond. And in that case, when you will do the numbering, you have to give low number, that is as minimum number as possible to this carbon which is that is part of this double bond or triple. Okay. And the IUPAC name of any halogen derivative, it is always written as one word. So in the previous case, what you have seen, it is two separate words, but now it is different. It should be written as one word. So now we will see all the IUPAC names of the same molecules. Now CH3Cl, first you have to write halo, so that is what is chloro, then methane, and there is no gap. Then bromo, you have to write first bromo and then ethane because it is two carbon. Now we have a branching in the third molecule. Remember, the third molecule is CH3, then 2CH3, and then there is Br. Now you have to choose the longest chain first. Now the longest chain should contain Br. So the longest chain will be like this: 1, 2, 3. So here you have two substituents at two positions. One is methyl substituent, another one is Br is already attached. Now among methyl and bromo, B comes before M alphabetically. So that is why first you will write 2 bromo hyphen 2 methyl, and then the longest chain is containing 3 carbon. So that is why it is ending with propane. So when we are doing this nomenclature, IUPAC nomenclature, basically we are considering this molecule as derivative of alkane. That is why the suffix we are using ANE, which is the suffix for alkane. Next molecule, CHCl3. Now CHCl3 is basically derivative of methane. Methane is CH4, but if you replace 3 hydrogen with 3 chlorine, now the structure will be Cl3CH. So this is basically, we write it in this way, CHCl3, but it is Cl3CH. Now here only one carbon present, and this one carbon is containing 3 chlorine. So you don't have to write the position because you have just one carbon. So simply we have to write trichloro because how many total number of halogen that you have to mention. So that is, it is trichloro. And as it is methane derivative, you have to end it with methane. ANE, that is the suffix for alkane. Next one, CH3CHBr2. Remember the structure? CH3CHBr. Now here longest chain is obviously these 2 carbon chain, and this is the one position because it is containing 2 bromine. So you have to start numbering from this carbon, and this is 2. So it is 1,1 dibromo because single carbon, that is same carbon, is containing 2 bromine. So that is why 1,1 dibromo, and as the longest chain is 2 carbon, so it is ending with ethane. And the last one, here longest chain is 3 carbon, but where from you will start the numbering? Remember, look at this rule. It is saying that if there is multiple bonds are present, that is unsaturations, it may be CC double bond or triple bond, then you have to give preference to that carbon which is in CC double. So that is why numbering will be started from here. 1, 2, 3. And at 3 position you have iodo, so that is, it is 3 iodo prop 1 in, because at 1 position there is double bond. So that is why it is prop 1 and then in. Okay. So in this way, here we have total 6 compounds, and we have seen both common names and as well as IUPAC names for all these same molecules, so that you can try to you can understand the difference between these two. Fine. So is there any doubt in this particular table?
No, ma'am.
Okay. Next we'll see some more examples under nomenclature of haloalkanes. In this table, again we have some molecules, their structural formula, then common name and IUPAC name. So CH3I, which is just like the previous example, remember it is CH3Cl, but now it is CH3I. That is the only difference. So it is methyl iodide, but IUPAC iodomethane. Then CH3CH2Br ethyl bromide, but it is bromoethyl. Next, we have 3 carbon chain and fluoro. So you have to start numbering here. This is 1, this is 2, and this is 3. But for common name, there is no such numbering. So it is simply N-propyl fluoride. But when it is IUPAC, you have to mention the number. It is 1 fluoro and then propane, because longest chain is 3 carbon. Next molecule is just see same number of carbon, hydrogen, fluorine. So it is actually the isomer of the third compound, right? Only the difference is here F is not present at the terminal carbon, but it is present at the middle carbon. So that is why it will be now 2 carbon. So 2 fluoropropane. But for common name, as this type of group, that is Me2CH, MECH, then another Me, and then some halogen is attached. So this group is basically isopropyl group. So that is why when you are writing the common name, what we have written isopropyl fluoride. Then the fifth one, it is very simple, 4 carbon chain in butyl. Why N? Because it is linear chain, there is no branching. But position of chlorine in case of IUPAC, it is 1, so that is it is 1 chlorobutane. Next molecule is also 4 carbon, but now we have methyl branching. So these two are basically isomer to each other. Only difference, now we have branching, and again we have Me2CH group, but total 4 carbon, so that is it is iso but not propyl. Here it is propyl, but it is isobutyl. And if it is IUPAC name, now it will be 1 chloro 2 methyl. Now the reason behind is because now it is 1, you have to give this carbon 1, because with this carbon chloro is attached. But we have also 2 position methyl group, methyl as substituent, so that is why 1 chloro 2 methyl. But chloro will be written first because C comes before M alphabetically. Next molecule, 4 carbon, but see, this is also isomer of the previous 2 compounds, but because you have total 4 carbon, only difference is now in the first 2 cases chlorine is attached to 1 degree carbon, now it is 2 degree carbon. And this is also that is butane derivative, but it is 2 chlorobutane, because this is 1 carbon, this is 2 carbon. And in case of common name, now this group is secondary butyl. Actually, when it is terminal carbon attached with halogen, it is N-butyl, but now it is secondary butyl, because the carbon with which chlorine is attached, this carbon is secondary carbon, but total number of carbon is 4, so that is why secondary butyl. Then the next one, this is also isomer of the previous one, because you have total 4 carbon, but now you have more branching, that is the difference. And 2 branching at that is this CH3 will be considered as substituent. This is also substituent, so the middle carbon is 2, so that is a 2 chloro 2 methyl, but it is tertiary chloride when it is common name. Next molecule is containing total 5 carbon, and this group is known as neopentyl. Now neopentyl and tertiary butyl, don't be confused between these two. These two are completely different. Tertiary butyl is total 4 carbon, and with this 3 degree carbon, with 3 degree because this carbon is attached to 3 more carbon, with this 3 degree carbon halogen is attached. But with this neopentyl, here also we have Me3C, but see the difference, this carbon is 3 degree, but CH2 carbon it is 1 degree. Okay, so this is Me3C CH2Br. Tertiary butyl is Me3CBr or Cl, whatever, but in this case it is Me3C and then another CH2 and then Br, and this group is known as neopentyl. But when it is IUPAC, now this is 1 carbon, 2 carbon, 3 carbon. So you have substituent 2 methyl substitute at 2 positions, so that is why 1 bromo, 2 dimethyl. Bromo is written first because B comes before M alphabetically. and 2 position there are 2 methyl, so 2 2 written twice, then dimethyl, but longest chain is total 3 carbon, so that is why it is ending with propane. Then we have CC11Cl, and this group is known as vinyl group, so that is why the common name is vinyl chloride, but IUPAC name will be chloroethene, ethene, not ethane, because it is CC double bond, unsaturation is present. And why we have not mentioned the position? Because both these carbon are equivalent. So even if you are writing one, actually that is not required. Even if you are not writing one, then also it is easily understandable from this name. Then the formula will be CH2 double bond CHCl. And the next one, this is 1, 2, 3, because double bonds will be given priority when you are numbering the carbon. So this is allyl bromide, this is 3-bromo propene. Now we will see some examples, but here we will have polyhalogen. That means more than one halogen atom will be there. CH2Cl, CH2Cl. Now when it is common name, you can write it in 2 ways. You can write it ethylene chloride or ethylene dichloride. But when it is IUPAC name, then this is 1 carbon, this is 2 carbon, 1, 2 dichloroethane. Because if you are not mentioning these numbers, when that is, if someone is seeing this IUPAC name and it is asked that write structure from this name, and if these 1, 2 are not mentioned, then how we will understand that whether both the carbon are attached to same carbon or two different carbons? So that is it is important to mention 1, 2. Fine. Now see, in the second molecule, this is also as if isomer of the previous one. These two are isomer, but here both the chlorine are attached to same carbon, so that is why now it is 1,1 dichloroethane. And in case of common name, now the group name is changed. It is now ethylidene. Try to understand difference. It is ethylene, it is ethylidene. Fine. Then the third one, now here common name is not possible, because when you are moving towards more complex structure, there is no such name for this alkyl part. Because when we write common name, we simply write the term alkyl and then halide. But if the alkyl group is very complex, very large, with so many branching, then obviously now common name is not possible. Common name is possible only for simple and small molecules. So that is why now we do not have any common name, we only have IUPAC name. And IUPAC name, here total number of carbon 4, numbering should be from this carbon, because among these two types of halogen, chlorine, bromine, but which one is having higher atomic mass? Bromine is having higher atomic mass compared to chlorine. So that is why numbering, that is preference is given towards bromine. This is 1, then 2 and 3. So when you will write the name, whatever is the position of bromine, it is true that here it is 1, but don't think that we have written bromo because its position is 1. No, that is not the reason. We have written bromo first because B comes before C alphabetically. So even if it is 2 bromo, 1 chloro, then also bromo will be written first. Fine. So it is 1 bromo and 2 and 3 in both carbon there is chlorine. So that is why 2, 3 dichloro, and the longest chain is containing total 4 carbons. So it is ending with N, but it is butane. The next molecule, first you have to find the longest chain, and you have to find the longest chain in such a way so that it contains the halogens and maximum number of carbon must be there. Fine. So see, if we are starting the numbering 2, 3, 4, 5. Now at 2 position we have bromo, 3 position we have chloro, but we also have methyl substituent, right? So we have methyl substituent. This is methyl substituent. Okay. And 2 position bromo, 3 position chloro. And substituent methyl, it is at 2 position and also at 4 position. Fine. So how we will write the name? It is total 3 types of substituent: bromo, chloro, methyl. So B will come before C, C will come before M. So that is why 2 bromo first, then 3 chloro, and 2, 4 both position methyl. So it will be 2, 4 dimethyl, and the longest chain is containing total 5 carbon. So that is why without giving any gap, it will be pentane. So again it is ending with N because it is alkane derivative. There is no CC double bond. So these two tables, is there any doubt?
No, ma'am.
Next we'll see a problem. Here a molecule is given, its structure is given, and we have to write the IUPAC name. Now this is carbon, this is carbon, this is also carbon. So CH3, then CH double bond, CCH3, then CH3Br. Now remember, when there is CC double or triple bond present, you have to give more preference. When you are doing the numbering to the carbon, you have to give more preference to this bond. So that is why numbering will be started in such a way so that this carbon is getting minimum number. So this is 1, this is 2, and the longest chain, it should also contain the CC double bond. That also you have to keep in mind. This is 4 and this is 5. So total number of carbon in the longest chain, 5. Here 4 position is containing this bromine. At 3 position there is methyl substituent. Okay, and all these carbons, they are part of the main parent chain. So it is 4 bromo, 3 methyl. So B will come before M. See, its position number is high. 4 is greater than 3, but still bromo you have to write first because it is alphabetically coming first. And at 2 position there is double bond. So that is why after 3 methyl it is pent hyphen 2-ene. Now it is not alkane derivative, right? So that is why we cannot end the name with the suffix "-ene". "-ene" is for alkane, but in this case it is not "-ene", it is "-ene" because it is alkene. Fine. So 4 bromo, 3 methyl, pent 2-ene. Is there any doubt?
No, ma'am.
Now after finishing the nomenclature of haloalkane, next we will see what is the nomenclature for haloarene. So now aromatic ring will be present and halogen atoms will be directly attached to the aromatic ring. Aryl halides are named by prefixing. Prefixing means the term with which you start the naming, the first word, that is prefix. Suffix is the last term. So prefixing halo to the name of parent aromatic hydrocarbon. If there is more than one substituent on the ring, suppose you have 2 chlorine or 1 chloro, 1 bromo like this, then you have to use the mathematical numerals, not Roman numerals, mathematical numerals, 1, 2, 1, 3 or 1, 4, because there are only this type of positions are possible, not anything else, right? So 1, 2 position, 1, 3 position. So 1, 2 is basically ortho, this is meta, this is para. In the common system, common naming system, relative position of 2 groups is shown by prefix ortho meta para. So ortho meta para for 1, 2, 1, 3, 1, 4, you cannot use in IUPAC. When it is IUPAC, you have to write 1, 2, 1, 3, 1. But mostly we say ortho meta para, but that is actually under common system, not IUPAC. And if it is monohalogen, for monohalogen substituted derivatives of benzene, common and IUPAC names both will be same. Now look at these examples. The first 3 examples, they are mono substituted, monohalo substituted. And see, here only one term is given. You can call it common system name or IUPAC system name, both are same. First you have to write the halo, chloro, bromo or iodo, and then you write benzene. Now in the second row, here we have dihalo. And look, it is position 1, 2, which is ortho. This is 1, 3, meta. This is 1, 4. Now when 2 terms are there, the first one, it is based on IUPAC. So it will be 1, 2 dibromobenzene. But if it is common system, now you have to write ortho dibromobenzene. Similarly for the middle one, ortho sorry, meta-dichlorobenzene, but IUPAC is 1,3-dichlorobenzene. And similarly, here it is para-dichloro, this is 1,4-dichloro. Fine. And now in the last row, we have some different types of molecule. It is true that it is monohalogen, but there are some other groups present in that, right? And in the second molecule, this is actually not haloarene. Why? Because bromine is not directly attached to aromatic ring. This is actually aliphatic halogen compound. Fine. So it is PHCH2Br, and PHCH2Br, that group, this group is known as benzyl group. So see here in the common system, we have written benzyl bromide. But when we have written the IUPAC name, it is phenyl bromomethane. So here the naming that we have done, it is basically just like the same system that we follow, we have seen in the last slide. So it is actually methane derivative. Methane is CH4. Suppose you have replaced one hydrogen with bromine, another hydrogen of methane with pH group. That means it is phenyl bromomethane, and we don't have to mention any position because you have just one carbon. So no question of mentioning the position. And for this molecule, it is toluene derivative because toluene is CH3 attached to benzene. This system is known as toluene. And as it is toluene derivative, so it is 3-chlorotoluene. Suppose if it is not containing any methyl, it will be simply 3-chlorobenzene, right? Actually, if it is, there is no CH3, even if it will not be 3, because with respect to which we will say 3. There must be some group, otherwise position doesn't matter anything. So see here, it is only one halogen, so no position we have mentioned. But in this case, there is methyl group, which is at 3 position. So that is why, that is with respect to methyl, chloro is 3 position. That is, it is 3-chlorotoluene. But if it is common name, it will be metachlorotoluene. Okay. Write the structure of the following halogen compounds. So here we have two names. See, if you look at the name carefully, the first name is ending with benzene. That means it is haloarene. It has to be because it is ending with benzene. But the second name, phenyl ring, it is present as a substituent within bracket. But actually this is aliphatic molecule because you have to just look at the suffix. Here suffix is ending with ane. That means it is alkane. So the first molecule, how we will write it? A. 1-bromo 4-secondary butyl. Butyl is 4 carbon. But when we say secondary, when the substituent is attached to secondary carbon, then it will be secondary butyl. So 1-bromo 4-secondary butyl 2-methyl benzene. So first of all, what you will do, as here suffix is benzene, simply write benzene. Okay. Then any position, write bromine. With respect to bromine, at 4 position there is secondary butyl group, and at 2 position there is methyl. So at 2 position you can write methyl, and at 4 position secondary butyl. Now secondary butyl means it will be like this. See, total number of carbon at 4 position with respect to bromine, it is 4 carbon. But the carbon with which this benzene ring is attached, this carbon is basically 2-degree carbon, because this carbon is attached to 2 more carbon. So that is, it is secondary butyl. But so if it is simply mentioned butyl, then the chain will be like this: benzene ring and then 4 carbon chain. Simple. Terminal position you have attached. But here, as it is mentioned secondary butyl, so this should be the connection point. Fine. So 1-bromo 2-methyl 4-secondary butyl benzene. Now the second one. So whenever you are getting this type of name and you have to write the structure, the simplest thing you can do, as it is ending with octane, oct means total 8 carbon. It is alkane and 8 carbon, 1, 2, 3, 4, 5, 6, 7, 8. Now here at one position we have iron group. So this is 1, 2, 3, 4, 5, 6, 7. One position iodine means you can write iodine, very simple. And at two position there is a substituent, but within substituent there is still again some sub numbering. I'm saying sub numbering means this is actual numbering, but within substituent there is further some number. This is at two position. So at two position there will be two chlorophenyl. So first write at two position there is some phenyl group, and at the connection point this will be 1, and I am writing here prime because we have already used 1 here. So you cannot write 1 again. So suppose it is 1 prime. So these two positions will be 2 prime, and at 2 position there is chloro. So it will be like this. Fine. So 2 chlorophenyl. So this is the total group, 2 chlorophenyl. But 2 chlorophenyl is again attached to at 2 position. So that is why another 2. And then at 1 position iodine, and total number of carbon is 8. So it is ending with octet. Is there any doubt? Should I repeat any part? Next question. What should be the correct IUPAC name for diethyl bromomethane? So here basically a name is given. There is no structure given. A particular name is given, but in options also you have name. But try to understand the difference between these two names. The name that is given in the question, that is basically a common name. But the names that are given in the options, that are IUPAC. That is the difference. Now first what you will do? You will draw the structure diethyl bromomethane. Methane, that means only one carbon is there. So methane CH4, but diethyl, that means two ethyl substituent are attached to the single carbon, and also bromo is attached. So it will be like this, two ethyl group attached, also bromo attached. So carbon valency 4, so the fourth position there will be hydrogen. Okay, so this is actually the molecule. Now look at the options. The first option is saying 1 bromo, 1 diethoxy. But here we do not have any oxygen, and ethoxy means OET group, OCH2, CH3. But this is not possible because we do not have any ethoxy. So this is not correct. Then 3 bromopropane. Now, if you look at this structure that I have drawn, if you do the numbering, it is 1, 2, 3, 4, 5. So at 3 position you have bromo, and the longest chain is total 5 carbon. So it is 3 bromopentane. This is actually the correct option. But why 3 and 4 are not correct? 3 is saying that it is 1 bromo, 1 ethyl propane. But here this name cannot be correct because as if it is considering this carbon as 1 carbon, and then at 1 carbon you have this ethyl group, and this is the longest chain. But that cannot be correct. Longest chain is 5 carbon. Longest chain cannot be containing 3 carbon. So that is why number 3 option is also wrong. And 1 bromopentane, option 4. If you actually draw this molecule, it will be something like this. This is 5 carbon, that is pentane. And at 1 position bromo. So this is the structure. But in our structure, bromine is attached to the middle carbon, not the terminal carbon. So this is also not correct. Correct option is option 2. Fine. What is the correct IUPAC naming for the molecule CHF2 CBrClF? So how many carbons are there? You have only 2 carbons. 1, 2. So it is better you first write the structure. So the first carbon is attached to 2 fluorine, 1 hydrogen, and the second carbon is attached to 1 bromine, 1 chlorine, 1 fluoro. Now the next question arises, as there are total 2 carbon, and which carbon we should give number 1? Which carbon will be getting the preference? Now the carbon with which 3 halogens are attached, that will be getting the preference because there are 3 halogens are attached. So this is 1 and this is 2. Now at one position you have bromo, you have chloro, and at 2 position and 1 position you have total 3 fluoro, 3F. Fine. Now among these 3 substituents, if you consider alphabetical order, B will come first, then C for chloro, B for bromo, C for chloro, F for fluoro. So B, C, F. This is the order, alphabetical. So bromine will be first. But see, if you just focus on this part, actually it will not help you much, because if you look at the options, in all the options, bromo is first. So better we focus next on the numbering. The carbon with which bromine is attached, this is actually number 1 carbon. So these 2 options cannot be correct because it is 2 bromo. Now among option A and B, if you look at the suffix, you can easily choose which option correct, because in option B, it is ending with ENE. But actually this molecule, there is no CC double bond. Both the carbon are sp3 hybridized, both carbon, right? So it is actually alkane. So suffix cannot be in, suffix will be ANE. So just based on this information, you can choose that the first option is correct, because in both option A and B, position numbers are same. Yes, it is first one, correct. So in both the options, it is 1, 1, 1, 2, 2. So based on that, you can't do anything. You have to focus on the suffix. So whenever you are seeing both options are almost same, you just have to search that portion of the name where it is different. So in these 2 options, only the difference is in this part, and that will help you to choose the correct option. Fine. This is the correct. So here the reason is also mentioned. Choose the carbon bonded to BrClF, that is the right hand side carbon, to be the first carbon, because it has the most non-hydrogen substituent on it. So it is not just for halogen. We are discussing it in this chapter because it is all about haloalkane and haloarene. But this rule is also applicable if you have any other substituent. So choose that carbon as the first carbon where maximum substituents are given, because our purpose is always to give the substituent as minimum number as possible. So that is why that carbon where maximum substituents are present, that should be the first carbon. Okay. Now we have a cyclic structure. There is 2 halogen, and very interestingly there are CC double bond also. Okay. You have to write the IUPAC name of the compound. It is cyclobutane derivative, but it is not alkane, it is alkene. So better we say it is actually cyclobutene, cyclo as well as butene. But look at this, all are ending with cyclobutene, but there are some positions, either 1 or 2. Now remember the rule. It is true that when there is no CC double bond, you give preference to the halogen. Numbering should be done where the halogen atoms are present. But when you have double bond, you have to give the double bonds or triple bond priority, more priority compared to halogen. So that is why now the numbering, it will be that is the number 1, that will be given according to the preference of CC double. Fine. Now, if we are writing here, this is 1. Because this carbon, it is part of CC double bond and also it is containing the halogen F. Fine. Now, among F and Cl, C comes before, that is chloro and fluoro. C comes before fluorine alphabetically. So, whatever is the position of chlorine, it will be always written first. So, it is 2 chloro, 1 fluoro, then cyclo, but, 1. So, the basic structure here is cyclobutene. And in this cyclic alkene, the position of double bond, it is not just for cyclic structure, we have also seen it before, that position of the CC double bond, or that is any multiple bond, it will always be getting the more preference. Fine. So it is 2 position, there is chloro, it will be mentioned first, then 1 fluoro, and double bond position is also 1, so that is why it is cyclobute 1-ene. Any doubt?
No, ma'am.
Next question, here a structure is given, we have to find the IUPAC name. Now, first thing that we have to do to find out the longest chain. And here if you are simply thinking this is the longest chain, this is wrong, because see here you have 2 carbon and you have to start numbering from that carbon which is containing halogen. So this should be number 1. This is number 2. But the number 3 carbon, this is not number 3 carbon. Number 3 carbon will be here and then 4. Fine. Now obviously it is 1 bromo, because among these 2 substituents, you have 2 substituents, methyl and bromo. So B will come before M. So bromo you have to write first. So this cannot be the correct option. Okay. So it will be 1 bromo. But longest chain is containing how many carbon? Total 4 carbon. So it should be ending with butane. But look at option A and B. It is ending with propane. Option B ending with ethane. So these 2 are also not correct. So 1 bromo 2 methyl butane. That will be the correct option. So see here this ethyl group, we have written it in extended form so that you can understand the numbering. 1, 2, 3, 4. And this is substituent at 2 position. Bromine is also substituent but at 1 position. Bromine will be written first because it is alphabetically, B comes before M, and then it is ending with butane. Fine. So after finishing the nomenclature topic, next we'll see parameters that are related to the nature of CX bond. Now why we are focusing on these parameters that are related to the nature of CX bond? Because haloalkane that you are basically getting from alkane. What you are doing? You are just replacing the one of the hydrogen of alkane and you are getting some haloalkane. So just take the example of CH4. If you replace one carbon hydrogen, now it will be CH3X, where X is any halogen. Now as you have replaced CH bond with CX bond, so obviously these 2 bonds, their nature are different, because H and X there is huge difference based on electronegativity. Fine. So because of, as we have changed this CH bond to CX, obviously there will be huge effect on the properties. So we will see those parameters that are related to this nature of CX bond. It is essential to understand the nature of CX bond because this determines the reactivity of haloalkane and haloarene. So if you have proper idea about these parameters, then only you can easily understand their chemical behavior, right? So that is why, that is the purpose we are discussing these parameters. Now if we compare the electronegativity of 4 halogen atoms, F, Cl, Br and I. We know F is the most electronegative, and all these halogens, they are basically from group 17. In group 17, as we are moving down, F, Cl, Br, I. So as we are moving down, electronegativity decreases. That you can see here, 3.98, 3.16, 2.96, 2.6. So these are the electronegativity values for halogen. And what about carbon's electronegativity? It is 2.55. So compared to any halogen, carbon is comparatively more electropositive, right? So whatever is the nature of halogen, whenever you will have any CX bond, partial positive charge will be towards carbon because it is less electronegative, and partial negative charge will be towards halogen because it is more electronegative. And this is the reason why this CX bond is polar in nature, because of this electronegativity difference. Now, if you keep the alkyl part constant, suppose if the molecule is that is R3CX. So if this part is constant, you are just changing F to Cl to Br to I. Obviously, when it is carbon-fluorine bond, then polarity will be maximum because electronegativity difference is maximum. If you take the difference 3.98, 2.55, and then if you change to the value 3.1, obviously the difference is decreasing. So the gap between these two values are high, and that is higher is this difference, higher will be the polarity, and that is the reason CF bond is the most polar among all these four carbon halogen bond. That is CF, CCl, CBr, Ci. So this is the polarity. You can see here whatever is the nature of these other three groups, carbon will always be towards the positive side, because whatever is the nature of X, FCl, Bri, carbon is always more electropositive comparatively. Now here we have taken four molecules: methyl fluoride, methyl chloride, methyl bromide, methyl. And here we will see the bond length of carbon fluorine, that is bond length. Here it is mentioned bond length in picometer, but which bond? It is carbon halogen bond. Now carbon halogen, when it is carbon fluorine, obviously the distance is minimum because fluorine is smallest. Both fluorine and carbon, they are from same period. Then when you switch to CCl, now the gap between C and Cl is increasing because chlorine is from third period and carbon from second. Then bromine from fourth period, gradually this is increasing and this is very high, maximum. So this is the bond length values in picometer. And when bond length is increasing, bond enthalpy, that is bond strain, that will be decreasing because these two are inversely related. Suppose there is a bond between A and B. So if the gap between A and B, suppose it is like this, but if A and B, the gap is very, very high, that means now you can easily break this bond. So when the distance is high, you can easily break this bond, and easily break means what? You have to provide less energy. So shorter is the bond distance, higher will be the bond enthalpy. So that is why see, as their bond length is minimum, bond enthalpy in kilojoule per mole unit, that is maximum, and gradually it is decreasing. And in the last column we have polarity of bond of which bond? CX bond in T by unit, that is the unit for dipole moment. And see maximum value, that is for CF. As you are moving to Cl to Br, the values are gradually decreasing. That is the dipole moment value. Because dipole moment value, that is directly related to the electronegativity difference. When this X is F, the difference between electronegativity maximum, that means charge separation will be maximum, right? So that is why this is having maximum dipole moment. Here we also have a picture. This is the picture for CH3Cl. So we have total 3 H attached to carbon and 1 Cl. So here carbon is sp3 hybridized. So carbon is using is 4 sp3, that is 3 sp3 it is using for bond formation with 3 hydrogen. So this is 1s of hydrogen, 1s of another hydrogen, 1s of third hydrogen. And the fourth sp3 orbital, that is used for bond formation, sigma bond formation with chlorine, and chlorine is using its p orbital. It will be 3p because it is from group period 3. So this is the basic structure. It is sp3 hybridized, so obviously it will be tetrahedral, and even if it is CH3AF or CH3Br, in all these cases it is tetrahedral because it is sp3 hybridized. Only this p orbital will be changing. So when it is fluorine, it is 2p, for chlorine 3p, for bromine 4p, and for iodine is 5. Okay, so this is the general structure, though here we have structure of CH3Cl, but for others also it will be more or less same, though there will be some difference in the angle. Standard angle is 109 degree for tetrahedral, but there may be slight deviation plus minus when you are changing the halogen. Okay, so this is the structure, and here we have seen bond length, bond energy, and dipole moment, how these are changing when we are changing the halogen atom. Now based on this CX bond nature, now we will see some physical properties. Some differences in properties can be seen as we move down the group in the homologous series of haloalkanes or haloarenes. So down the group means as you are moving from F to Cl to Br to I, basically you are moving down group 17. So keeping the alkyl part same, suppose you have Rx haloalkane or ARX haloarene. So keeping this R fixed or AR fixed, suppose you are just changing the X, you are moving down the group F, Cl, Br in the homologous series, that is keeping this part constant. So obviously there will be difference in their physical properties, and the reason is as you are moving down F to Cl to Br, atomic mass is increasing, and when atomic mass is increasing, overall molar mass is also increasing. So that is why there will be some difference in physical properties. First point we have here, physical state, that is whether it is solid, liquid, or gaseous. Those haloalkanes where you have only one carbon, that is methyl derivative or ethyl or propyl, up to 3 carbon, they are actually gaseous state. Their nature under normal temperature, normal condition, it is gaseous in nature. But whenever you are crossing the value 3, suppose halogen is fixed, you are just changing the number of carbon. So when you are moving beyond 3, now gradually their nature will be from gaseous to liquid to solid. And it has to be, because when you are changing the number of carbon, basically you are increasing the number of carbon. So alkyl part is increasing. Suppose halogen is fixed. The first alkyl group R1F, second one R2F, then R3F. So keeping the halogen part fixed, when you are changing this number, I mean a carbon number. Suppose here you have 2 carbon, here you have 4 carbon, here we have 10 carbon. So obviously as you are moving towards higher number of carbon in the alkyl part, mass will be increasing, overall molar mass. So that is why now the nature will be shifting from gaseous state to liquid or solid. Fine. So first it will be gaseous, then gradually it will be moving towards liquid physical state, and finally when the mass is very high, it will be ultimately solid. Color. When they are in pure condition, suppose you have pure haloalkane sample, it is colorless. But that is very ideal condition. Mostly it will not be so. Especially for bromo and iodo haloalkane if you have. And if you cannot keep it in the dark, suppose some presence of light is there, and that is natural mostly. So there will be some color generation. And what is the reason behind this color generation? What will happen? When it is in presence of light, light will help for this type of reaction that you are seeing here. Here Ri bond will be broken, there will be decomposition, and 2 R group are now attached together, they will form alkane, and iodine is also generated. And we know that free iodine, that is a diatomic molecule, which is basically solid, but it has also some vapor form which is violet in color. So because of this generation of I2, and when it is RBr, there will be generation of Br2. Now these are having some color. So development of color is basically because of this type of reaction, which is possible only in presence of light. So that is why they are mostly kept in dark bottle, out far from light. But if it is not possible, then gradually there will be color formation that will take place. Okay. Boiling point and melting point. Haloalkanes have higher boiling point and melting point than the parent alkane. So parent alkane, suppose you have C2H6 and now you have CH3, CH2F. So this is parent alkane and this is the corresponding fluorine derivative. So there will be change in BP and MP. BP means boiling point. This is melting point, and it will be high compared to the parent alkane. Having same number of carbons, that is, if you are keeping this alkyl part same, that is, we have not changed the carbon, we have just replaced one H with F. So carbon number same. What happens now? Intermolecular forces of attraction are stronger in haloalkane. So when it is simply alkane, it is basically carbon and hydrogen. Suppose X number of carbon and Y number of hydrogen. Okay. So when there is only carbon hydrogen, there will be no dipole present, because charge separation between carbon and hydrogen is not so high, which is high comparatively in case of CX bond. Now when CX bond is polar, because of this electronegativity difference between C and X, so now because of this charge separation, there will be individual molecules will be behaving as if it is a dipole, and between two molecules, that is between two dipole, there will be interaction, that is why it is dipole-dipole interaction. But this is not possible when it is simply hydrocarbon, that is simply alkane. So that is why now, because of this intermolecular force dipole-dipole interaction, as it is stronger, so you have to provide more energy. So BP and MP both are high. BP MP high means what? When you are converting the solid to liquid, that is MP. When you are converting from liquid to vapor, it is BP. And you have to break this interaction, and higher is the strength of this interaction, higher will be the energy that you have to provide. So that is why MP, BP both are high. And the boiling point, melting point of haloalkanes decreases with respect to halogen in the following order. That means keeping the alkyl part same. If you are changing the halogen, obviously this is the order. It is decreasing, and it has to be because atomic mass is decreasing. Atomic mass decreasing means van der Waals interaction will also decrease, and MP, BP both will be decreasing. Boiling point of chlorobromoiodoalkane increases with increase in number of halogen. Now keeping the same halogen and number of carbon is same, what you are doing, you are just changing the number of halogen. Here you have 4 chlorine, then 1 hydrogen, 3 chlorine, 2 hydrogen, 2 chlorine, 3 hydrogen, 1. So this is the order. Here also same reason. Molar mass when high, then in van der Waals interaction high. As a result, BP, MP will be high. And the boiling point, melting point of monoalkane increases with increase in the number of carbon. So keeping the number of halogen same and keeping the halogen nature same, if you are changing the number of carbon, then also the mass of this alkyl chain is increasing. It is 3 carbon, it is 2 carbon, it is 1. So again, because of increase in molar mass, boiling point and melting point is increasing. Okay. Next day we will discuss some more physical properties. We will end the session here. If there is any doubt, please mention.
No, ma'am.
So thank you for listening. We are ending the session here.
Thank you, ma'am.